Day. Not everybody woke up.
Yeah.
I think it has to do with this camera and the video. We have the video, right? So I wake up. What's that? So I know we're doing stuff that's not for the meter. That's why I expect most of you to not really pay attention to this in terms of homework and stuff until after the meter. That's fine. Meter means tomorrow. Room shield 1. Room, I think it's on 5. Is that correct? And my computer is not connected to this network. Not sure I updated or not the website. Okay. So I think it's supposed to be there now. So make sure it is. One second. What about this? Okay, done. So they should be there for whoever misses the class. 10 a.m. up to dynamic programming, no hashes. before I move on to hashing and trees, the stuff that's in your next homework, somebody proposed at office hours a meter problem, right? Was it you? The breakup into the strings, breakup? Yeah, yeah. So that's CLRS, I think, was it 5, 9? 15, 9. That says a string is given. Let's say it's x1, x2, up to xm. And it needs to be broken up into parts. So also the breaks are given. Those are a bunch of indices at which index I want to break the string. So it could be B1, B2, up to Bk. The intention of this is to obtain the following strings. If I take this, the goal is to get x1 all the way up to xb1 break. The break tells me where I need to break the string. Then the other one is x, it be b1 plus 1 up to x b2 break. Then it be x b2 plus 1 up to x b3, so on and so forth. And the last one will be x bk plus 1 up to the last xm. So I want to break this string into parts. The breaks are given, where to break it. But the break cost, penalty. So every time I'm breaking an array from xi to xj, a chunk of the array, I'm breaking after spot b, this is b and this is b plus 1. The cost of this operation is the difference j minus I, the length of the string. So it makes a difference in what order I do the breaks. Initially, the first break, no matter what I do, it will cost me m operations, because any break costs the length of the string. But then once I break it, the next break, right, suppose I break it here, the next break will cost this, and the other breaks in here will cost that. So it matters if you look at that problem 5.9, it makes a difference whether I do B1 first and then B2 and then B3, or B3 first and then B2 and then B1, and so on and so forth. Right? So the algorithm asks for the optimal, meaning minimum penalty total order of breaks. Again, the string is given, the breaks are given. It's not a question of where to break it, it's a question in what order we perform the breaks. Okay. Similar if you want to matrix multiplication. In there we had the matrices, we had the multiplication order. There was no question who is going to multiply with who. The only question was in what order do we perform these multiplications. You guys remember the matrix chain multiplication problem? All right. So a cute problem. Something's gonna happen tomorrow, so that's a candidate. I'm gonna try to be at office hours today. I can't promise that, but I'm gonna try to be there. This last minute questions will be so. In here, the exam is designed for 4 hours. 4 hours, 6 questions, but you can stay longer. So we won't have a hard limit time on the exam. People bring sandwiches, coffee, everything that makes you comfortable. The room is booked for many hours. We're probably not gonna stay later than, I don't know, let's say this is 4 hours, double that will be 8 hours. So if we start at 10 plus 8, 6 p.m., probably at 6 p.m. we'll go home. I'm just saying, I don't want you to have a time pressure on you, okay? So you'll have enough time to solve the problems. You will not have enough time to study the chapters that you didn't study if you don't understand quicksort. There'll be not enough time during the exam to understand quicksort. Okay. So now what I want to do is to move on with stuff that you need for your next homework. I think some of this stuff is due over the spring break. I have to refix those deadlines. You have two homeworks. One is pure recapping data structures from undergraduate, stacks, queues, so on and so forth. And you even have to write a summary of like a 1-page or 2-page summary of the main points that you see. You don't have to recap it from the book. If you like to study stacks and queue from somewhere else, you can recap that material. And then you have some exercises about hashes and trees that require implementation. So like before, the grade for those will come by demoing your code to a TA. Okay? So where were we? We're at hash tables. And so we said we have the idea is that we have a bunch of key values, right? Key I, value I, from I equal 1 to n. How we manage those things? We have a hashing function that takes a key and produces an index. You can call it catalog index. This is between max and 1, 0. It's up to you. Maybe smaller than max. So the way we thought about this, here's my catalog. And every time I get a key, I map it. This here, it's h of key. It gives me the position from 0 to max minus 1 of where I want to go in here. And so this is literally an index, like 12 or 15 or 25. And what h of key, let's follow our, this is an array. Let's follow our notation. Let me organize this a little bit different. So I have a key. H of the key is here. That's the index. H of key. And what do I store in here, in this position? This is a pointer. It points to some memory object that stores the key and value. And if I have another key, key 2, that has some other value, 2, that happens to match, so if h of key 1 is h of key 2, they will have the same index. So that means they correspond to the same spot in the catalog. This catalog stores the address of the beginning of a linked list, so I can chain the list with the keys and values that I observed. So what are the advantages of a hash? Number one, the key range can be enormous. As in 10 to the 20. Nevertheless, the index range is manageable. So even though my keys range, the possible keys could be people's names or, I don't know, diseases or emails or whatever else I have, and that could be a gigantic space. I'm not saying we have all the values in there. For every time we deal with a problem, we only have few names, but the set of possible names is very, very large. This range, which is 0 to max, is not that bad. It's always picked to be a reasonable, manageable size. For example, I would say if you are a university and you have to manage your students, including the previous students, right, you may end up with the number of IDs that you have to store there, a few million people. But you don't need a range more than 100,000 or even 50,000 slots for that. Okay? So that's very good. In the sense of programming, so assuming we hide the theory, right? You guys use hashes before? How many people use hashes in a programming language? Almost everybody, like I do that all the time. But you don't need to know all this to use a hash. You need to know this to build a back mechanism for a hash. But when you use a hash in Java or Python, you trust that whoever implemented it knew what they're doing, right? Well, in programming, what's the appearance of a hash? How does it look to us? We say things like h of some key, right, equals some value, right? So it has the same form in many ways like an array, similar to array syntax. I don't mean this mathematically. I mean when you actually use a hash, you write things like h of that key is that value. This is a Perl notation, but I'm sure there's a Python one, a Java one, so on and so forth. What's the difference programmatically? What's the biggest advantage of a hash versus an array? I'm talking not about the back end. This is a theoretical advantage, right? I mean, I don't mean it's just theoretical. I mean, it has to do with the efficiency of implementation. I mean, assuming, say, my index, my key range is not so big, why can't I do this with an array? What prevents me in Java or MATLAB or Python or anything to write this with an array?
Arrays are bounded.
Hmm?
Arrays are bounded. Like, they're kind of bounded space. Your key can
Right,
be
so
bounded.
assuming the range of keys is not that big. So I didn't formulate this question properly because the question is easy. The main advantage in a programmatically, without thinking of the range, is that those keys could be anything. So the main advantage keys, anything. Anything that can be represented in memory, of course, because I need a handle to what I have in my memory. But in an array, what do I need the keys to be? Numbers. Now you can argue anything is a number in the computer memory because everything is in memory. You can read it as an integer, even if it's a name or an address or whatever. But in that case, the range tends to be very big, right? We looked at this last time. If you really want to take some string and treat this as a number, so a string may have 20 to 50 characters. Each character is 8 bits. If I have 50 characters, that's 400 bits. If I really want to treat 400 bits as an integer, I could do that. But the range of that integer is gigantic, right? It's 2 to the 400. So it's not easy to take words or names or anything else and treat them like keys in an array, right? I mean, there are all kinds of form of lookup tables and dictionaries that try to implement this, but hashes have an immediate advantage that they can do this with a syntax that's very similar to arrays. So it's not like you have to do something very different. It's again, what you see is what you get if you understand arrays. And they manage the backend very efficiently. If you only have 5 words, they don't declare a memory space that's much bigger than what's necessary, right? Okay, and another things that we talked about last time, like we had collisions. Those are from an h of a key I, it's the same as h of key j. So they both correspond same index. In a collision, how do we solve it? We do chaining. Chaining means this. We have to store the keys one after the other. And then we have operations like insert, update, and delete, etc. All operations require the main basic operation a hash table is? One is hashing, right? I have to compute h of a key. We assume that that is instant. It's not really instant, but let's say it's instant. The reason it's not instant, we're gonna get to it in a second. But what was the other operation that's absolutely needed to do anything in a hash?
Hashing function.
So I compute a hash, I get the key, I get hash of the key, that's the index. But then if I want to insert, update, delete, what do I have to do? Search this list, right? So search the list at h of key. And we said successful or unsuccessful searches are roughly how computationally expensive? 1 plus, what was that constant there? N divided by max. So once you have those two things, hashing and searching in the list, it's relatively easy once you find a spot to update, delete, insert. Because in a linked list, those operations are pretty straightforward, right? So delete will be what? Take this object out, remake the pointers. Update means rewrite a different value in that key, right? Insert, if I really want to put something here, insert it. If you prepare for some data you don't know, like you have some key value pairs and you don't know those values. It could be patients, it could be emails, it could be words in a document, it could be, I don't know, houses, who knows what. And now you are a programmer, not in the algorithms class. Where would you insert a value? So you have an insert operation. You don't know what those keys, you write your hash mechanism, right? The back end of the hash. That's what you have to do for the homework. But once you have it, you don't know, you give it to Virgil. Virgil's going to use it to hash his data, but you don't know what that data is. So if you would do that, where would you insert a new key value pair? So you compute h of key, of course, you get h of key, and now you can probably insert it anywhere you want in this list. What would be some good heuristics for where to insert it in the list? Why in the beginning?
Because it's pointer, you can just break the pointer, like point to next element and next element going to the original.
Right, you argue that I can insert it in the beginning. Yeah, but why would I insert it in the beginning and not in the middle or in the end?
The runtime.
The runtime would be faster to insert in the beginning, right? Because once I get to this spot, if I know it's an insert, I don't have to traverse the list. But that usually doesn't happen. Usually in data, he's right. If I know for sure it's an insert, why bother traversing the list? I can just put in the beginning, right? But in principle, you have a key, it's hard to avoid the search. Because in most data and most problems, once you get a key, you don't know if you need to insert it or if it's already there, you need to update it. Things you count the words in a document. That's a very typical hashing exercise. That's the exercise you guys have for the homework. When you get the word, how do you know you have it or not? You have to traverse this list, right? Many languages offer an API that says if this key exists, well, can we avoid the search? How do we know it exists? We can easily check if the index exists, right? So computing h of key, that's O of 1. And we can tell, how do we know if the index has been used or not? It's either some value or? No. But if it's a value, now we don't know if the key we have in our hand is the one in the list or not, assuming collisions can happen, right? It could be a different key. So it's kind of hard to avoid the traversing of this list. That's why this is the fundamental theorem in the hashing chapter, like how long does it take to search for keys? So while he's right, if I know for sure it's an insert, very likely I still have to look for it in most data problems. But suppose I do look for it now. So I do look for it. Presumably, if the key is there, insert means really update a value, because I found that word again, I increased the count, something like that. But suppose I really go through the list and I didn't find it. Right? So it's not there. I really have to insert it. Now, is there advantage, since I already processed the list, to insert in the beginning versus middle versus the end? No computational advantage, but use a different heuristic. Where would you insert it? Again, you're designing a hash table, and you're gonna, this is the backend mechanism of a hash, and you're gonna give it to me, and I'm gonna use it for my data. And you don't know what kind of data I have. Where would you insert it? This is not a theoretical question, it's just a guess hunch. Would you still insert in the beginning a new key? Why? Or why at the end? Or why in the middle? So we already traversed the list and we already know we didn't find it, so we need to put it in. Where should we put it?
I would say in the beginning, because I would say probably it's more likely that that key would reoccur recently because it just came in.
Well, he just said has a name. I store something in the beginning or where it's easier access because I'm thinking if you just use that key somehow, it's likely that you're gonna see it soon again. What name does that has in computer science? It's like caching or move to front by saying processors do that all the time. A lot of speed up in modern CPUs comes from exactly this thing. I use a register for some operation that you have. I save that in the front of the memory so that I'm thinking if you use that value or that register, you're probably gonna use it again. Now that's not true all the time, I'm just making a guess, right? But if you use it again, I have it quickly in my fast memory. Your processors have a layer memory, there's a super fast memory that allows operations, kind of middle fast and very slow, and then there's the RAM, which is the slowest, and then there's the hard drive. So the higher in the stack data goes, some value or some entrance, the faster it is for the processor to use it. It keeps the recent data there exactly because of this principle. If you use this value, maybe you're going to use it again. So why would I want that? If I put that in the beginning, and I still did my search, right? I did my search, I did a 1 plus of alpha there, I put in the beginning. If, soon I'm going to see this value again, why is that good to be in the beginning? Searching will be faster, right? Because everything in the beginning will take closer to constant time than anything average, which is O of 1 over max. Right? One more thing about this. How do we think about this value, n by max? Who's n? So, who's n? Number of keys. So n is the number of keys. Not to be confused, number of actual keys. Not to be confused with the size of the key range. You know, I've seen this mistake before when people think of this value and say, what are the possible words in English language? There's 300,000, right? So my keys are 300,000. That's not n. That's the range of the keys. When I'm processing a document, I won't see all 300,000 words in it, right? So n for a document might be only 10,000 words, the words that I actually see. And what's max? Max is whatever is convenient for my index. So if I process documents, this n for each document might be 10,000 words, but for my entire collection of documents might be all 300,000 words. And max might be 20,000 or something like that, whatever is convenient for my index. So when you design a hash, you have to think about this ratio. What do I want to be convenient for my memory operations? How much this max should be? Most computers will handle max up to 1 million or even 10 million very, very easily. Because declaring an array, this is just a value of pointers, so declaring an array of 10 million pointers is no big deal for any computer. And you gotta think of this, when you know what kind of application you're gonna have. How many keys am I dealing with here? All right, so kind of that's what we've done. We also talked about hashing functions. So assuming a key representation is read as an integer, that causes this blow up of the range. If I could have few words that are written in few bytes, but if I read the whole thing as integers, I'm ending up with ranges that are astronomically large. So I'm really talking about use the memory representation of a key, and from bit 1 to bit, I don't know, t, if I read this whole thing as an integer, that's I can't deal with that range. I can deal with one of these memory bit strings, right? But I won't be able to deal with all of them as a range. The first hash function we did was h of a key was what? Was some m was n times key more m max. So if I take key as an integer, I think we wrote it down as key bar as the integer cast of key. If I do modulo m, where is this going to be now? It's 0, 1, up to max minus 1. And for these purposes, max should not be close to 2 at the power. I think it's pretty easy to see that if I take modulo, I get an index in the range that I want. The other option was h of a key written down as ceiling of max times fractional part of Ka. Fractional means take only the after the decimal point, whatever. So this fractional part can be written as Ka minus the floor of Ka, right? Because if I take a number and I take the integer out, I'm left to the fractional part of it, right? In other words, 123.456, the fractional of this number is 0.456. So the book has a little explanation for how to do this operation very efficiently. In here, we would use max a power of 2, and we would use a some integer s divided by 2 to the w, and we really want to think of memory units of W bits. So you know how we define the formats for integers: long, int, short, so on and so forth. And we say short is so many bits, long is so many bits. So like unsigned int, how many bits is that in most programming languages? Hmm? 8 or 16, right? Short is? I think short is 16. The typical int, when I declare an int, how many bits? Typically. Depends on the language, but most languages, when you say integer, give you how many bytes or bits? 4 bytes, right? So that's 32 bits. When you say long, how many bits it gives you? 64? Right? So there are different formats. What I mean to say is that let's assume the format is on W bits. That could be 16 or 32 or something like that. Here's how this operation can be computed then. We first multiply k with s. That would be, so operations. K times A. So A is this, but we're going to multiply also with 2 a W. So that's going to give me K and S. So now, this is a 2W bit sequence. So here's how I'm going to think about it. There are 2 chunks of W bits each. So K is the key, sorry. So K is an integer, S is an integer. A is not an integer. A is this S divided by 2 to the W. Right? So if I multiply the key with S, S being an integer, how many bits do I get? So let's assume that K fits on W bits, meaning if I declare my integers being 32 bits, keys are also 32 bits or long, or shorter. So what happens when I multiply those 2 things here? I say I'm getting something that's at most 2 W bits. And not just that, I can write this result, K times S here, as R1 times 2 to the W plus R0. So I'm looking for a numeration base that's effectively 2 a W. For some of you, it might be easier to see this as W is 4. In each case, this is 2 to the 4, 16, right? So if this is my result on 2W bits, I have written something that this is R0 and this is R1, effectively, right? Because that's how numeration bases work. It says this is the part that you represent on the last unit. Think about base 16 again. How does the digits in base 16 work? If this is something times 16, that something goes to the first unit, right? And R0 is the last unit. So what I meant to say, how much is A5 in base 16? It's A times 16 plus 5, right? In any base. So think about this in that sense. If this is a 2W bit sequence, And if I assume my numeration base is 2 to the W, meaning every digit has W bits, how many digits I have here? 2 digits. Right? This is 2 digits of W bits each. The effective numeration base will be 2 to the W here. Like if I have 4 bits, the numeration base will be 16. If I have 8 bits, the numeration base will be 256. So what happens is, first of all, when I do this operation, I'm getting something that's two units of W bits each. And then I can write this as 1 unit, that's R1, and another unit, that's R0. Where is my result? Where do I get now my answer here? Max, so I only did K times A times W, so that's K times S. But what I really want is the fractional part of Ka times max, right? So let's think about this for a second. Where is this answer I'm looking for? Everybody with me here, what's going on? So I've started with the key, that's an integer. I'm supposed to multiply with this rational number A, but A has this form. A is some integer divided by 2 to the W. Instead of multiplying with A, I multiply with A and 2 to the W. So I get T times S. Now that's an integer multiplication, it's easy to do. This is a 2 times W bit vector. So it's gonna look like that. There'll be some representation on the first W bits, some representation on the other W bits. Now, how do you divide? Now I multiply with this 2 to the W, which is too much. If I divide with it, what happens when we divide with the numeration base? If I take a number in base 16 and I divide with 16, what happens to the bits? There's a shift, right? So this dividing by 2 to the W, it's a shift. And if max is a power, how do I multiply with max? If max is a power of 2, that's another shift, right? So I say the answer I'm looking for are the P bits in here. P bits from the max. If I read the first P bits of this thing here, that is this whole answer. So this will be the integer created by first P significant bits in R0. Those ones here. So the reason this is important is that this is a very fast operation as compared to multiplying rational numbers in base 10 or base 2. If you think about it this way, there's only one multiplication, that's 2 integers, and then looking at that representation of bits, taking this particular P bits is a O of 1 type of operation, right? Once I have my bits, just say, take those ones, read it as an integer, that's a fast operation. But I'm gonna leave it at this. I want you guys to think about, is that really those P bits corresponding to this operation? Like maybe take an example first, like I started there. Take an A that's 2 to the 4, something divided to the 4. Take a max, maybe that's 100 or so, 128, be a power of 2. Take some key, say 15 or 12 or 25. Do this multiplication and see, do I get the bits here exactly the answer I'm looking for? Those P bits. So P comes from the power of max. W comes from what? It's how I think of A. It's, if S is an integer, W is how many spots do I move the dot in A, right? If A has in base 2 4 decimals, in base 2, then W has to be 4, right? If I want A with 20 decimals, I need W to be 20. If I want A to be only 1 decimal, so everything is either integer or half of an integer, then I want W to be? Did I stun you guys with this thing? So if I want A's to be either integer or integer 0.5, I need this W to be 1, right? Because I'm only going to divide by 2. If I want the 0.25's values, divide by 4. If I want 0.125 values, divide by 8. Right? So that determines the W, and max determines how many bits do I chunk out of it. In general, designing hash functions has two parts. There's a conceptual part, which is what do I want a hash function? So a good hash function has a property. The probability of collisions ki equal with h of kj, probability of this collision should be about what's a good hash function? One that puts, I may have to have collisions if the number of keys is bigger than number of indexes. I'm going to have collisions, right? Because pigeonhole principle says 2 keys will go to the same index. Fine. But I don't want them to go distributed, skewed. A lot of collisions in one index and then some other index free. So how do I say I want them to be distributed? The probability of 2 of them colliding should be 1 over max. Roughly. That's a uniform distribution of collisions. Of course, I expect to have collisions. If I have 100,000 keys and 10,000 slots, on average I get 10 keys per index. I don't want these values to be far away from 10. I want all indexes to have about 10 collisions. So there's two parts in designing a hash function. One is trying to do the randomness part. So hash function design. One part is to do distribute collisions. Requires domain knowledge. It would be a lot easier to determine this if you know what kind of data you have. Do you have strings? Do you have IDs? Do you have patients? Do you have numbers? What are the keys? Helps a lot. In the slides, I give an example of how to do it for text. If you go to the, not the book, but the slides, there is, if I have hash of a word, so if my keys are words. Now words, of course, are represented as ASCII characters, right? So for every letter, there's 8 bits. How do you design a hash function that avoids systematic collisions? As in, I don't want a lot of words to be mapped to the same index, right? That's what you're going to have to do for the homework. I want a hash function that takes any word and produces an index, but I don't want a lot of words to map to the same index, because that means a lot of collisions in one spot. So there are some versions of take every ASCII code, which is a number between 0 and 256, square them, take some modulo, multiply them, do all kinds of operations that that will facilitate randomness of the index you get. And then there is engineering. You want H to be a fast computation. So even if I design the function, the hashing function correctly, question is how do I get it to operate fast? Like this is saying, if this is the function you want, you probably don't want to multiply fractional numbers and take the floors. You want to implement something like this on bits, much faster operation. So now back to my initial point, which is why hashing is not exactly a constant time operation. Hashing, calling the hash function, say 4 words. Why is really not constant? I mean, for practical purpose, it might be constant, but in general, it has to go over the memory length of the whatever you have, right? If the memory length is fixed, say I'm only dealing with numbers of 400 bits or shorter, then I know my hash function will probably have to go through 400 bits and calculate some integer as a result of it. But people are using hashes even for things that are way longer than 400 bits, right? Every time you put a piece of text as a hash key, like a sentence, ever did NLP, natural language processing, and you store an entire string that could be the whole sentence as a key, that sentence is far longer than 400 bits, right? 400 bits give me only 50 characters, right? So if I start using strings or arbitrary length, say characters, can I do that? Is there a problem in my hashing mechanisms if my keys are very long? Suppose I use entire paragraphs or entire pages. The whole page, the whole text of the page is one key. What's the problem? I mean, is there any problem here? Can I do that? I'm going to call the hash function. It's going to give me an integer. And then I use it normal. So that's a great advantage of hashes, actually, right? That I can use keys that, in terms of memory representation, they're very large, if I want to, if I need to. And the hashing mechanism, collision, search, update, delete, all that is going to work. But the hashing function, if it has to go through a chunk of memory, it will have to spend more time than the constant amount of time. So hashing is not exactly constant, like absolutely constant, and it depends of the values you have. So in theoretical questions, like people have tried to use hashes for the homework problems and for the midterm problems and so on and so forth, it's going to have to do with how many bits the keys has and how the hash function is implemented. Like you can argue of certain designs like this one, how long this operation is going to take. Well, what do? I multiply 2 integers of W bits each. So how long would that take? When I multiply 2 integers of W bits each. You have to compute that, right? And then, how long does it take to put my hands on these P bits? Log of P, maybe? Maybe longer, I don't know. What I'm saying is, if you know this is my hash function, and my keys fit on W bits, and my M is P bits, and I choose those values, maybe a W that makes sense is 4 if you know your keys are 32 bits integers. And then P may be something like, I know I want an S value. I have to design this in advance. There's some suggestions what is a good A. So suppose I choose this P to be 8, right? Actually, P has to be smaller than W, so if I want, okay, so I get W of 32, a P equal 8, right? Then I can tell how long the function is going to take if I implement this particular function. I need to multiply 2 32 bits integers and then chop off 8 bits out of this. That's going to be constant for this design. If W is fixed, P is fixed in here, that's going to be constant for all keys that have 4 bits integers. But the problem with this design, again, this has been an interview question in some form of another that's saying, if I use a particular hash design, not this one, and I decide W fixed and P fixed, is this a constant time operation? Once I fix W and P? Yes. Once I fix W and P, this is a certain operation. It's only going to take so much time. What's the problem with fixing a W? Can I have arbitrary long keys now? No. So arbitrary long keys are a bit longer than 32 bits integers. Right? If I want to use sentences as my ID, sentences don't fit in 32 bits. So that won't work for keys that are longer. I would need a much larger W to allow for arbitrary text to happen. So in practice, of course, what you notice when you program is the hashing is almost a constant time operation. But in reality, it depends what keys you have. Okay, one more thing about this is if I tell you this is my function, and you can guess quite easily what's the W and P, right? Because you can say, are you using this? I think your W is 32 bits, because your keys are probably on 32 bits. And I'm guessing that your P is about 8 or so. You are an adversary. How would you make my life difficult? So my job, I'm a developer, and I implement this hashing mechanism, right? And now you want to prove, or you want to demonstrate that my hashing is very slow. You know my hash function. You know I'm using this hash function with W of 32 and P equal 8. What kind of data will you create? So if you really are one of these pain in the ass people who says, okay, I'm going to take what you have and I want to screw it up. If you know my hash function, how would you screw it up?
Generate same P bits for different various keys.
So generate a bunch of data with keys that have what you're
Same
looking
P
for.
bits, which will result P bits.
Which will result in what?
More bits.
So an adversary that wants to give a hard time to a hash design will create a data where a lot of keys colliding into one index, right? The power of hashes, assuming a decent design, it depends on the number of collisions. What happens if all the keys go to one spot? What's a hash effectively now? Not an array, it's a linked list. So the hash, if there's a lot of collisions, the hash becomes a linked list. A linked list can be very inefficient for some operations, right? So if you're an adversary and you know the hash function, adversary, generate keys that collide in few indexes. Generate many keys that collide in few indexes. Right? So this is a kind of a cat and mouse game. I'm the one who designs the hash function. That's what programming languages implementations do, right? In Python, I can assure you there's a backend mechanism that implements hashing functions, correct? Otherwise, how would hashing work? In Java, there is a mechanism that implements this, in MATLAB and all languages, right? An adversary comes and say, if I look at that mechanism, I can really give it a hard time, because I can, once I know your hash function, I can get a lot of keys that have this problem. But now I'm back to Java and say, how can I prevent this to happen? In other words, I want to put up a design, and I think from a commercial standpoint, I'm shipping it. Like, I'm giving the new Java update to people. They install it on their computers. At that point, I have no power of changing anything. Once you install my Java on your computer or my Python, I can't go tell you, oh, you have this data set. That was an adversary. Change the hash function. I can't do that because you already have Java installed. How can I do something so that whatever the adversary does, and not gonna be able to mess up my hash. What can I do? Part of my mechanism to say any adversary that tries to create a lot of collisions is not gonna be able to do that easily.
Changing the P.
If my hash function is fixed and the adversary knows it, there's nothing I can do. Because once you know the hash function and you know for sure that's the hash function is being used, you can generate keys that hash to the same spot, right? So what can I do? I'm the designer now.
Change the hash function whenever there is lot of it.
I can't do that in the middle of the data. Once I notice their collisions, means I'm already programming, somebody's using to implement a database or an Excel sheet or whatever, right? I can't in the middle of the code to say change your hash function. The whole table is gonna go like to trash, right? So you have to start from the beginning. What I can do is what? So what he's saying, start with your hash function. Notice that you have a lot of collisions and tell the user, hey buddy, sorry, you're gonna have to start from the beginning with a different hash function because this one is not good for you. Users will be unhappy, right? But the idea is not bad.
Maybe run two of them together.
Two hash functions,
Yeah, and it should be such that one
generate
is
two
handling
tables and see if you have a lot of collisions. But again, if my adversary knows both hash functions, maybe there's a way to generate keys now to mess up both of them. Maybe. But you guys get in the right direction. What else can I do? Hmm?
Double hash.
What if I have a lot of hash functions? I don't design one. I design many. Right? Many hash functions. The problem is when you, the user, run the code, when the hash function has to be decided. So every time I run a code, I build a hash for whatever purpose. The hash function has to be fixed. Right? So when the moment you say, I'm going to hash something, like my users, my dates, my diseases, whatever, I pick a hash function. Could be this one. But then I can't change it during that execution, during that hash built in memory, right? But what I can do is the initial selection of the hash function could be not set in stone. Every time you say declare a hash, because most languages you have to say this data structure is a hash, right? They can say, if you want a hash, I'm going to choose a hash function from a large collection at random. Okay? So why would I choose one at random and not decide from the beginning I want this hash function? Because if the hash function is deterministic, my adversary is going to know which hash function I'm using. But if I pick on one at random, he's not going to know which hash function I'm using. In other words, what's the exact sequence of design here, of events? So universal hashing. I'm the designer, creates a family of hash functions. Not just one, an entire collection of them. So let's call that H, like around H. So these are all hash functions. And let's say the size of this size of this H we'll have to think about later. That's the first thing. Then a user gets data, possibly from an adversary. Wants to do a hash. So the data is now given, right? If you decided I'm going to hash something, it means you have the data already that you want to hash. One hash function is picked at random. But once it's picked, it's going to be used as the hash function. And now I use the hash table. Meaning, if you decide tomorrow to build a different hash for a different data set, what's going to happen? You're going to choose a different hash function at random from that set. So we want the same thing. The property here is that if I pick an h at random, we want, there's a magic property, probability of that h. H is now random. hi of a key I, probability of key I mapping the same as key j. We want this to be around 1 over max or smaller than 1 over max. This is the property we've been discussing before. We want the collisions to distribute. So what we are saying is, if the adversary would know my hash function, it would create a really bad data set for me. But it doesn't know, maybe it knows the entire collection of hash functions, but it wouldn't know which hash function I'm going to pick. Are you guys with me? So the adversary knows the collection of hash functions. The question is now, can the adversary, looking at all these hash functions, create a data set? What would adversary want to do here? He would like to create a data set such that for any hash function being picked, there's a lot of collisions. And what would I want to do? I want to create a hash set of functions such that if you pick one at random, no matter how bad the data, no matter how intentionally badly the data is created, I don't get a lot of collisions. So who's going to win? Can I design such big H? This is called a universal set. Can I design such a set that no matter the data, some hash functions will be terrible, but if you pick one at random, maybe some hash functions will be terrible, some hash functions will be good. Having one good function is not good enough because I'm going to pick it at random. I can't do what he says. Look at the data. Once you look at the data, choose the proper hash function. That'll be easy. I'm going to say I want to pick one at random without seeing the data and to have this nice property that I won't get, on average, so many collisions. Maybe every once in a while I get really unlucky and I pick the hash function that's going to do terrible. But on average, I don't want to have many collisions. So this is possible. This H is possible. For example, I won't make any proofs here. You can read from the book. For example, a Hamming family of functions that is 2 parameters, H, A, B. H, A, B is A times the key plus B modulo max, modulo another mod, max. So this is similar to the first hash function we saw. It's a modulo, but I'm choosing a P. P is a large prime. And I'm saying for any A and B smaller than P, I'm going to pick a random hash function that computes A times the key is the integer key, plus B, modulo P, and then I'm going to take modulo max. That's very similar to the first. Modulo max is from here. What I'm saying is that initially I compute something that's what's being chosen at random here, P is fixed, but at random is this A and B. So when I build the hash, the first thing I'm saying, choose an A and B. And there's two things here. You have to know number theory for those two. One is, I can compute this very fast. If you studied RSA before, you know that certain operations with numbers, even though they're very, very, very big, key can be very big, A can be very big, P can be very big, but these kind of operations can be computed very fast. The only thing that we don't know how to do and how cryptography works is what? What operations we cannot compute very fast on large numbers. If we would break cryptography in the banks. We can do exponentials very fast. There's one operation that the whole cryptography relies on that's hard to do. We think, we're not sure, we hope it's hard. Modulo is easy, addition, multiplication, division, exponentiation is easy. Factorization is hard, which is if I give you a number, find the product of factors that give you that number. That's hard. We're going to study this at the end of the term, cryptography a little bit. But all these operations, even those are large numbers, are easy to do. And to prove that this hash has this property, meaning no matter who designs the data, no matter how bad, if I pick one random function from here, I have this property. That's proven in the book. So there's a theorem relying a little bit of number theory that says, if I pick one such function at random, doesn't matter how the adversary did. If you give me the worst possible set of keys, I still have a nice collision property on average. So this is a very good thing to do. It's not just an adversary. I give you this extreme example. If somebody wants to make my life hard on purpose, but it may be not an adversary, maybe some data keys property that I'm not aware of. And when I design hashes, I can't know what people are going to use those hashes for, right? So this is a very useful idea to say, pick from this universe, good universe of functions, pick one at random every time you build a hash. That even though I'm not dealing with adversarial data, I still guarantee, on average, good hashing properties. Be very careful about this chapter, because I've seen lately in interviews a lot of questions, variations of hashing questions. I know you guys are gonna very soon look for jobs, internships, and there's two kinds of algorithmic questions. Of course, you have to do the programming part. They're gonna give you a program and you have to do the programming. I can't help you with that because I'm not a programmer. But there is the thinking type of questions, you know. Those numbers do this and that, find a way to find the missing number, da 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 da. The kind of things that we did for sorting, dynamic programming questions. But I've seen questions about hashes, advantages, disadvantages, why a hash function is good, why is it bad, when is it good, when is it bad, how to deal with data that has the following property, collisions, caching, move to front things. So I think you should really take a hard look at hashing and hashing questions, because I've seen some questions about this. What happens is a lot of people use hashes without thinking about them. Oh, it's just going to work for me, right? Because it always does. And then recruiters love these questions because they think correctly that most people use hashes without having a clue what's going on. Most people understand arrays and linked lists, exactly what's going on, but not hashes. So before going to interviews, take a hard look at that. Okay, that's what I have to say about hashing. You're gonna have a hashing homework. The other thing that I have to say, yes?
I have a question. So if you hash the same value twice, you get a different value, hash value, right?
No.
Based on
Once
that.
you pick a hash function, if h is fixed, if I choose a hash function, anytime I hash a key, I'm gonna get the same exact value.
Once you have
Fix
chosen
the
that.
hash.
Right.
So for a particular hash table, I have to stick with one function. I can't change, that's what he asked. I can't change the hash function while I'm still operating on that hash table. In other words, if I build a hash table and then I store it on the hard drive, like serialize it, when I load it back, I have to use the same hash function. But for a different hash table, I can use a different function, right? Or for tomorrow, even if I hash the same data set tomorrow again from scratch, like I use it in memory and then I shut down my computer, memory is gone, right? Tomorrow I hash the same data again. I don't have to use the same function like yesterday. But it's a good question. We're emphasizing one point here. Once I choose a hash function, the whole operations on that hash table have to use that hash function. If I decided that that hash function is no good for whatever reason, and I choose to use a different one, what does that mean? I have to rebuild the hash from scratch. Okay? So that don't be confusing here. It's the same hashing thing. The hash function is settled, nailed down for all operations on that hash. But for a new hash or for the same data hash rebuilt from scratch, I could use a different function. And I have this universal set of functions that I can always choose one at random from every time I'm starting a new hash. But once I pick the function, all operations on that hash has to be through this function. Okay? So it is possible to get unlucky. I pick a random function, and it's exactly the hash function that my adversary designed the data against. Then I'm going to have a very, very bad hash properties for that one hash. But next day, next month, next year, when I pick new random functions, I won't always have the bad choice hash function. Okay. The other thing you guys need for the homework, red-black trees. I'm gonna treat this more like an engineering type of question. So I won't teach a lot of red-black trees, although if everybody gets stuck, I'm willing to spend a lecture after. You guys know the next week there's no classes, right? So I'm willing to spend a lecture on this if people have a lot of questions. But this is really a simple conceptual thing that you have to understand, and a difficult, heavy engineering thing that you have to implement. So I do not plan to help you with the engineering aspect, but I will tell you a little bit how to think about it. If we find an HDMI cable somewhere, nope. Good to have one, but there is no lot of USB cables. Here. So I want to give a quick intro. We only have 15 minutes. And again, the difficulty, it won't be at all into this find a way to turn the lights on. So these are some slides related to hash table. The only slide I want to point out here. So really, this is how you wanna think of a of a hash, you wanna, when you, for yourself, when you think of a hash, you typically know the keys that you're gonna have. I mean, you don't know the exact keys, but you know their people's names. So this is how you wanna imagine a hash looking like. The only thing that I have here that's not in a book, it's an example for how would you think of a hash for how hashing works, right? Like that's the homework you're gonna have. So if you, for every word you're gonna have to see, you're gonna say count that word or store the positions or some value. So what would be an appropriate hashing function that would work for words and will give, you don't have to be perfectly uniform. We say we like collisions to be uniform over my catalog. The real problem is what? It's not that they are not exactly uniform. The real problem is one index that has a lot of collisions. You know, even though they're not perfectly equal, if say the ratio between the longest chain, the longest list, and the shortest list is not more than 5, that's okay. The real problem is when I have a bunch of indexes empty and some index is extremely long. So there's no real concern here that they're not exactly uniform. The real concern is what's the size of my longest list. If that size is half of the data, that's bad. Okay? So in here I want to talk about red-black trees. I'm assuming people already know binary search trees. If I want to print this array sorted, it's stored in a binary search tree. What order should I use? How do I parse this tree? In order, which is left node, right, recursively, right? I can do this recursively, left node, right, and I print the whole thing. If I want mean, all the way to the left, do I ever go right? No. If I want max, all the way to the right. And if I want successor, I pick a value and I say, I want successor means the next immediate highest value. Well, that can be either down. So if there is a value down here, is that the successor? You're going to have to implement this function successor, like for real, and you have to demonstrate to TA that it works. If I have a value here, what that value, can that value be 6.5? No. Can it be 5? That'll be the successor. So what happens if I have a value here and then an entire tree under? I go to the right, the successor is on the right, and then left. What happens if there's no value here? I go up and then how much to the right? All the way to the root? So why do I say this? Do I want to teach you where to find a successor right now? No. I want to tell you that successor, it's something that at least half of the students get it wrong the first time. I got it wrong the first time. Okay? So I don't think it's complicated enough to get an interview question about successors, but I'm just warning you, most people get the successor and predecessor, which is the opposite one, wrong the first time. It could be down here and all the way to the left, or up there and you have to figure out where to go up. In other words, if 6 is the left child of 15, we have to stop. But what if 6 is the right child of somebody? When we go up, should we go further up? Or not? To find the successor. So make sure you think about this on paper before you implement successor and predecessor. Because implementation is not hard once you know where to go. Okay? So of course the problems with binary search trees, they are very nice, very efficient, if they are balanced. That is, we want the most paths to be of length log n. We don't like the paths that are roughly linear. Linear paths create effectively lists, and those are bad. So the whole point of red-black trees is to balance the tree. So what we're going to add is this color, red and black. And the essential properties is that if a node is red, then the children are black. And for any path, the number of black, path means from root to a leaf, the number of black nodes is the same. So did you guys remember those two properties? What's the first one? If a node is red, children black. And on every path, the number of black nodes is the same, or roughly the same. Would this enforce balance? Those two properties. The number of black nodes on every path, it's a fixed 5. In this, how many black nodes are on every path? 3, right? Starting with the root. And for every red, both children have to be black. Would that enforce, can I have a really unbalanced tree? Can I have a path now that's half of the data? If I have a long path, at least half of it have to be black nodes. What property tells me this? Why can't I have a lot of red on that path? There is so one of those two properties says if you have a long path, half of it must be black. What the property is? Every red node has to have black children. You can't have a lot of red because for every red, the children has to be black. So now why this path can't be that long if half of it must be black? Why it can't be very long? Because all paths have the same amount of black. So the blacks are balanced in the tree. If this will be n by 2, the whole path, how much black would I have there? N by 4. Can I have n by 4 on all paths? No, that's too many nodes. Right? So the blacks are balancing the tree, and then the reds can only be the size of blacks, because for every red I need to have black. I can't have a large arbitrary sequence of reds. How many people with me? Okay, let's say it again. For every red, children are black, and the amount of blacks is balanced on all paths. Doesn't have to be exactly like the book says, exactly the same amount, but if this balanced, the whole tree will have to be balanced. So there's a theorem that says this. If you have those two properties, there's some additional stuff in here, but if you have those two properties, you cannot have an unbalanced binary search tree. For exactly this reason, unbalanced means a long path. A long path means at least half of it is black. If half of it is black, it means all paths have to have that much black, which is a contradiction, because in a binary search tree, to have all black having n by 4, all paths having n by 4 black would be way too many nodes. Okay? So now that we understand the theory, we want to maintain this balancing property, right? What's going to happen? A lot of the search, mean, mass, successor, predecessor operations that you implement on a regular tree have nothing to do with these colors. Wherever you find the min, max search or arranged by the sorting property, you can ignore the colors. What are the things that are going to mess up the coloring? Insertion and deletion, right? When I insert a node, it's not merely obvious how to make the tree balance. Remember the two balancing properties? Every red must have blacks, and the number of blacks have to be roughly the same. So what's happening is that when we insert things or delete things, we do it normally, like binary search, find a spot, insert the value, but then we have to fix the balance. So this is how it looks. Insertion requires 3 fixes. The fixes are written here. Deletion, which is complicated. In many years I made deletion an extra credit exercise because students have a super hard time with it, and TAs try to implement it also super hard time with it. But some people did succeed. It's possible to succeed. If you spend the whole week, the whole spring break doing deletion fixing, yeah, you're gonna get it. Very good exercise for trees. So deletion is a problem. It has 4 fixing cases. The book has a long pseudocode. If you follow it truly, you get it right. Now, that's the part that you have to figure out at engineering. The part that you have to understand now that there is a magic unit, a magic fixing that you would implement first as an auxiliary function, and all those other fixes rely on that function. Here's what that is. It's called rotation. It says if my tree looks like this, it's not about colors. So ignore red and black for a moment. If my tree looks like this, y, there's some chunk, some path coming to y here. Y is at the root, x is on the left, this is alpha, beta, gamma. They denote entire subtrees. So alpha is a whole subtree, beta is a whole subtree. What this rotation to the right does, so what happened? X became the top. You can imagine this as rotation to the right when I take x and y and I kind of move them like this. Alpha remains the left child of x. Gamma remains the right child of y. But beta, instead of being the right child of x, the whole subtree became the left child of y. This is still a valid binary search tree. That's a very important thing to recognize. The reason is, what is my relationship in this tree? Who's the smallest?
Alpha.
Alpha, meaning any element in alpha. What's next? X. What's next? Beta. What's next? And the largest? No. This is the same relationship on the right side. If this was true here, this was binary search valid tree, after the rotation, alpha, x, there's exactly the same relation. So if this was valid, the definition being everybody on the left is smaller than the node, and the node is smaller than everybody on the right side, not just the immediate children, everybody on the right subtree, then the same thing will happen here. If you write down this relationship, you get exactly the same inequality. How many people see this? Okay? Hands up so I can see them. Good. So this is the first thing you implement. You first to design your tree structure with pointers or arrays, whatever you want to design your tree structure with. You can't use a built-in tree structure in Java or Python. You have to implement your own pointer tree, define objects and put pointers, whatever. You need these operations that says if I want to rotate x and y to the right, change the pointers to become this, and if I want to change this to the left, of course I do it to become that. And this will not violate the tree properties. It's still a binary search tree. Okay? Once you implement this, you go to, so this has some examples of rotations. What happens if I rotate here x to the y? Who's that subtree under y? This is the subtree, right? This whole subtree, instead of being the left subtree of y, becomes the right subtree of x. So when I insert, I think it's easier to follow the slides to understand what's going on, but then to follow the book pseudocode to actually implement the insertion fixes. Z parent is the parent of Z. Z uncle, what's an uncle? I go to my parent. Parent is clear, right? I go up. And then who's the uncle? The brother of the parent, right? Because the parent has some root, some parent, and that parent may have another child. It's a binary search tree, so there are most two children, right? So if Z is here, who's the parent? 5. Who's the uncle? The brother of 5. So there's few cases. If this happens, Z parent and uncle are red. Here's how you fix it. Now I would spend, this is easy to see what's going on with the visual. So I will go through the slides. The fixes are no big deal. Rotate, color, maybe recolor, this is say change the color. What's ZPP? See, parent, again parent. Says that make that one red, make this one black, that's just recoloring. And when I say advanced Z, I mean what? Recurrent, keep fixing the tree, right? I fix things here, and after this fix, I move Z to there. And now I may be, again, in one of the three cases that needs fixing. The hardest part here is to prove that in the end, this is all fixed up. That's not required for this class. What is required is for you to understand this particular fix. What is it doing? And to implement all three fixes. I did have a question in the final exam that was asking, what is the fix if this happens? Fix this tree. Okay, so that's not unreasonable, but the hard part in here at PhD level is to prove that if you execute those three fixes, Z will keep going up and up and up until it reaches the root. Prove that at that point, the whole tree is balanced. We have three cases here, and similarly, we have 4 problems with deletions. You delete a value, and then you have to fix the balance. There's going to be a lot of back and forth about this to get it right. Sometimes, again, we made deletion an extra credit exercise. If you do so, you can obtain all operations running log n time, which is what you want in a binary system. So I think for this, we'll give some, I don't know what the deadline is. So the deadline, you guys have 2 homeworks here. Simple structures is do some exercises. This is really undergraduate material. Each one of those takes on average like 3 minutes. Those are very simple. And you have to write a summary. Because we are a little tight and this is spring break, we'll probably make this due after. We'll make the homework simple data structure. Will be no help for that. That's recapping undergraduate material. So you have to do it over the spring break. But this other one, hash and trees implementation, we may push it for a week or so. So I'm going to change the deadline. For this one, you're going to have to implement a hash that counts words in text. You have to implement your own hash mechanism. And there's a DP problem here. So what happened to the, right, this is the red-black tree problem. So the first 2 questions are the ones that require implementations. The rest are extras. Maybe the DP problem is more relevant for right now, for tomorrow. So you're going to have to write some code for this exercise, and you have to demo to it. Okay? So tomorrow, 10 a.m., meter, with a lot of questions. Don't blame me, because you guys are the ones who propose these questions. I currently have, I'm still thinking what to put in, but there's at least 1 or 2 of the ones you said. So, interesting questions people have found. I would certainly expect some dynamic programming and some sorting in there. And recurrences. By the way, I made a lot of progress on that recurrence, the T of n minus 1, T of n by 2 plus something. So, did anybody solve it? No? I will have a solution by Sunday on it. Shillman, room 105 tomorrow.